we move on to chapter 3. Chapter 3 is called Derivative Topics. And so I've got a short list of what exactly that means. So we're going to see a couple of applications of derivatives. In this chapter, we're going to see more derivative shortcuts for more types of functions, getting more complex than just polynomials. And finally, we're going to see derivatives of non-functions. There will be a section, how do you take a derivative of something that's not a function? So that's pretty interesting. Okay, where this chapter begins in 3.1 is we probably categorize this in the applications. There's not going to be much calculus here. We're just gonna familiarize ourselves with this concept, and then we're gonna perform derivatives of it in 3.2. Okay, 3.1 is the number e, and this is not in itself technically new. You would have seen this in an algebra class. You see the number e when it comes to like exponential growth and decay. You learn it about the same time you learn about natural logs. Logarithms and natural logs and e all connect. Okay, so what is this? We're going to look at it from a deeper perspective, from a calculus perspective here. Here's the number e. So I have the number e here and then where it comes from. So if you put e, it should be in your scientific calculator. If you get the decimal version, I just wrote a few of the decimal places here. It's about 2.71828. And then that number will continue on with no pattern. The number e is very similar to pi. It's a decimal that goes on forever with no pattern to the digits. And you may have even seen this before in an algebra class, about what the approximation is for e, but you would not have seen where it comes from. So it turns out this is how e is defined. It's the limit as n approaches infinity for 1 plus 1 over n raised to the n. So the idea is as n gets larger and larger and larger, that value ends up going closer and closer to this number. And that's surprising, right? Kind of in one sense, you would think that as n gets bigger, right, it's an exponent. You would think maybe as the exponent gets bigger, this thing just goes to infinity. On the other hand, the n is also here. And 1 over a number that's getting bigger is going to go to 0. So, it's kind of unclear where this thing is, what might be going on. Although I would think, with that exponent, that this number is just going to get huge, and get larger and larger to infinity. But it turns out no, as n gets bigger, it levels off at this number here. So we can even kind of highlight that with this quick table. So if we were in class together, we would all work this out and just kind of convince ourselves, because it's not obvious at all that you would get this result for sure. What if n equals 1, right? If you plug in 1 to our expression 1 plus 1 over n to the n. Well, if you plug in 1, you'd have 1 plus 1 raised to the first, and that would be 2. Okay, big deal. What if you plug in 10? And now here you're definitely going to need to grab a calculator, right? 1 plus 1/10, all of that raised to the 10th. And you would get this, 2.59374246. That's all my calculator could present. What if you put in 100, right? N is getting bigger and bigger to infinity. If we go 100 for n, 1 plus 1 over 100, all raised to the 100, 2.704813829, and of course it would keep going, but my calculator screen runs out about right there. And hey, why stop at 100? Let's go to 1,000. 1 plus 1 over 1,000, all to the thousandths. 2.716923932, and we can see it here. It's leveling off, right? So it started at 2, then 2.5, almost 2.6, then it got to 2.7. You're like, okay, it's getting bigger. It is, but it's slowing down, right? There's about a 0.6 gap here, and there's only about a 0.1 gap here, and then here it only increases by like 0.01. right? So it's definitely not just getting bigger and bigger, but as we get larger and larger n's, it's going to keep getting bigger, but it's going to approach this number here. Okay, and that's the story of E. And kind of interesting note, it turns out we learn about E in algebra, yet it's got a basis in calculus. Nobody thought anything of the number E or recognized it until after calculus came around. And there's more to the story there, but it's kind of, we learn it, years before we ever do calculus, yet that's when it, that's when people realized that it was an important number. Okay, so what are we going to do in 3.1 with this number E? We are going to do some limits, but turns out that's at the end of the chapter. We're going to do much more non-calculus stuff, and no derivatives in this section at all. We're just kind of setting ourselves up for the next section. This may sound familiar, the compound interest formula. And I'll just read it. I got all these arrows everywhere. Let me just go ahead and read the formula. A equals P times the quantity 1 plus R over N, all raised to the NT. You would have seen that in a previous course. A stands for the amount, like the total amount in your account. P we call the principal. It's the initial amount of money that you would start with. The R, of course, is your interest rate, written as a decimal. N appears twice, there and there. That is the number of compoundings per year. So how many times is interest compounded? How many times is it applied throughout the year? And then finally, T is time, but we say it represents years. Okay. You may have also you would have learned about in a previous algebra course, continuously compounded interest. And here's the formula for continuously compounded interest. A equals PE to the RT. Much simpler formula, and we see the E there. Now let's connect the dots with what we've done so far in this section. What is going on with continuously compounded interest? So in regular compound interest, we have this variable N, but that does not appear in continuously compounded. Why? N represents the number of compoundings, right? But when we say continuously compounded, we're thinking there's always interest being applied at every moment. At every instant, interest is being compounded. Maybe back here, what if like N was 12, right? Interest is compounded 12 times per year. That's pretty common, right? Once a month. If you have a credit card, they charge you interest once a month if there's any interest to be charged. But, we could do more than that, right? We could charge interest every day, and it would be much less per day. But instead of every month, you could do it every day. Why stop there? You could charge interest every hour, every minute, every second. And continuously compounded interest is saying, okay, we're not even breaking it down into like seconds. Or we're going way past that. We're saying at every little instant of time, interest is being compounded. In other words, the number of compoundings per year goes to infinity. There's an infinite number of compoundings during the year because it's at every instant, and an instant is not a measurable amount of time. It's so tiny. Okay, so think about this formula, but as n approaches infinity, and compare that to the definition of E, right? And we can see it, right? 1 plus R over N raised to the N. Now there's also an R here and there's a T there, but that's the formula, right? And we're taking n to infinity. So we won't go through all the details about how this formula turns in to the continuously compound interest formula, but we really don't have to. We can see it, right? 1 plus 1 over n to the n. So that portion becomes the E, And what we're skipping is like maybe why the r pops out into the exponent. We will not look at those details. Obviously, the t will stay there. If that makes sense. Okay, kind of connecting the dots with some of your algebra. That's fun. What sort of problems are we going to look at? We're going to look at some of the same kind of problems that you may have had in an algebra class, and nothing wrong with that. So again, no calculus right now. For example, let's say $5,000 is invested at 6.1% compounded continuously. And part A asks, how much will it be worth after 4 years? Okay, so you're just going to take your $5,000, put it in the bank. It's going to earn 6.1% compounded continuously. So that's really nice. You're always earning interest at every given moment. So how much is it going to be worth after 4 years? So there'll be a lot of interest, of course, that gets added on. Well, we're going to go with our continuously compounded interest formula. We're looking for the amount. The initial investment, the principal, was $5,000. We've got the E. There's R, but we write it as a decimal, right? We convert it, so we move that decimal place over twice. 0.061 is our interest rate, and T is the number of years. So we're saying 4 years. And well, we can just put this whole thing, 5,000 E raised to the 0.061 times 4 into a calculator and get our answer. This is what I got. 6,381.72. One thing you want to be careful about here, order of operations. So when you put that in, my calculator's got the E button right there. So if I go 5,000 E 0.061, then I want to be sure there's parentheses there to get my answer. Okay. Nothing new there, but just being sure. All right, let's move on to part B. Same setup. We're still investing $5,000 at 6.1% compounded continuously. How many years until it is worth $7,000? Okay, so after 4 years, it got up to 63.81 and some cents. How many years would it take to get all the way up to 7,000? And this is a little bit harder, right? Because we're rearranging what we know. We don't have the time now. So we're going to say, okay, same formula, but this time we know the amount. We're after is 7,000. The principal is still 5,000. E raised to the 0.061. That's all the same, but now we're trying to find the value of T. Okay. So how are we going to start? To isolate the T, we need to begin by dividing by 5,000. Well, when we divide 5,000, we get all those zeros to cancel. 7 over 5 equals E raised to the 0.061 T. And here's a big question from your algebra review that we did at the beginning. How can we cancel out the E? And well, we use a natural log. Natural log and E are inverses, we say. So just ignore the final answer here for the moment. We're going to take the natural log of both sides. So this is a bit small, but that's the natural log of 7 over 5 equals the natural log of E to the 0.061 T. Okay. And the idea is the natural log and the E cancel. So we've got the natural log of 7 over 5 equals 0.061 T. And we're almost there. We can divide by that decimal. The natural log of 7 over 5 divided by 0.061 will equal our T. So at this point, we can grab our calculator. And that's what I got. For my final answer, I rounded to 2 decimal places. 5.52 years. And that makes sense. You know, it's more than 4 years, of course. Um, see, how much did they gain? After 4 years, they gained 381, or excuse me, 1,381. So if we want to gain another, was like about another 600 something dollars to get up to 7,000, you know, if it took 4 years to get this far, it makes sense it would take about another year and a half to get up to 7,000. Of course, as things grow this way, they grow faster and faster. So that answer seems very reasonable. Okay, no calculus though. All right, part C. This is a good one. How many years until it doubles in value? When we invest the 5,000 at 6.1% compounded continuously, how long will it take until it doubles? Well, what's the amount that we're after? Well, if it doubles, then that would be 10,000, right? So same setup, very similar setup to part B, except, well, we're looking for it to reach 10,000, starting at 5,000, e to the 0.061t. So we'll just divide that, cover up our answer. We'll just divide that 5,000 and get 2. Okay. Natural log to both sides. So if we take the natural log of 2, on the right side, the natural log of e would cancel out. And all we have is 0.061t. And we can divide that decimal. The natural log of 2 divided by 0.061 will equal t. And you'll get that answer right there, 11.36 years. Again, makes sense. You know, that seems pretty reasonable compared to our other numbers in the other parts. Hey, here's a question just to follow up. So here we started with 5,000 and wanted to get 10,000, right? Because we were doubling. Let me ask you this. Did it matter that we were starting at 5,000? Right? Would that change our answer to this problem? How many years until it doubles? No, right? If we change this initial amount, then the doubling would change as well. So maybe if we were starting with 1,000 and wanted to double, well, 1,000, then we'd put 2,000 here. And when we divide, we're still going to get 2. Here, actually, the only thing that's important is the interest rate, the 6.1%. That makes all the difference in how fast something will double. It doesn't matter what value you start with. Obviously, it'd be nicer if you start with more so that when you double, you get that much more gain. But here, it's not important that we started with 5,000. Kind of an interesting thing to note. Okay, let's stop this video here. More to come.